Okay, so there are different types of group action. Okay. So there are different types of group action. So the number one is that the group action can be transitive. So what does transitivity mean? It means that if, say, P1 and P2 are 2 points on your manifold, then there exists some G in the group such that P2 is going to be G acting on P1, I should say it, sorry, not like that. P2 should be G acting on P1. Okay. If this is true, then we say the group action is transitive. So what does transitivity really mean? It means that any point on the manifold can be reached by some group action, okay? That's basically what it means. If I start from any point, then any other point can be reached by some group action, okay? That's what transitivity means. Let's just discuss some examples, okay? So first, let me write the comments. You know, what it means is that, you know, any point on M can be reached from any other point by the group action. Okay. So can you give me an example of a group action that is transitive?
Multiplication in R-1 number line.
R-1.
R-0, real line -0.
So what is the group and what is the manifold that it is acting on? I mean, groups can act on themselves. That's true.
The group is R-0 and the manifold is same, the number line and the action.
I see, okay. Why are you going for R-1?
Sir, R-0 because 0 has no input.
Oh, I see. Right, right. But you could have said that, you know, the same thing about, say, the additive group, right? The additive group is also something that acts on itself, right? Yeah. Okay, good. So any other examples?
The Pauli group and multiplication.
Yeah, Pauli group is a discrete group. It's not a Lie group, right? But you're right. I mean, but we are not talking about discrete groups, Lie groups necessarily here. But actually we are talking about, you know, Lie groups. We are talking about actions on manifolds. So we are, yeah. I mean, these ideas can be generalized to other spaces too, but today we are talking about actions on manifolds. So you have to tell me what M is, you have to tell me what G is, right? How about, you know, the action of U1 on S1? So we know that the elements of U1, so U1 is the same thing as SO2, right? So an element of U1 can be written as e to the power I theta, where theta goes from 0 to 2 pi. Right, so now if I take the manifold S, which is the one sphere, that is the circle, right? So if I take a point, it can be any point, right? And I represent it by some vector. So this angle is giving me the coordinate of on S1. So this is S1, and phi is a coordinate on S1. Now, if I take an element of U1, so this is an element of U1, and I say, okay, what I do is that I define the action of U1 on S1 as sigma, the element of U1 is, say, e to the power I theta, and phi is the point on my S1, and I define that action to be e to the power I theta, e to the power I phi. Okay, then what does it do? It takes the point phi and it translates it to another point over here, such that the coordinate of the new point is phi plus theta, where theta, right? Where theta is this angle, right? So this is do you agree that this is a group action? I mean, we haven't verified, but it should be pretty clear that it's a group action, because if I go and say, okay, let's take the identity element, which is going to be just number 1 and phi, and then this is just e to the power I phi. So we see that phi doesn't change, right? And if I take phi e I theta 1 or theta 2 e I theta, and the sigma of e of theta 2 of phi, then I will have e to the power I theta 1 theta 2 acting on e to the I phi, which is going to be e to the power I theta 1 plus theta 2 acting on phi. All right, so we see that both of the group action postulates are satisfied, right? And we see that.
Could we write
Sorry?
sigma? Could we write sigma theta comma phi instead of e to the power I theta? Like, would that work, or we have to fix some exponential on the first one?
No, I mean, I'm just like using exponential to kind of give a shortcut notation. You don't have to use exponential, right? This can be done in many different ways. It can be done using 2x2 matrices. It can be done. I just think using complex numbers is very, very convenient.
Okay, got it.
Yeah. So, but the point that I want to make is that any point on the circle can be reached from any other point by some element of U1. Right?
Yes, sir.
Therefore, this action is transitive. Okay, so this is essentially the U1 version of what Farhan just said about the real line. Right, this is basically the same, but here we just have, we just have it as a circle. Now, of course, U1, you might think that maybe the fact that U1 is the same thing as the circle has something to do with this, and that's actually not true. And because of that, if we can take G to be SO3 and M to be the two-sphere, right? And the way that the two-sphere, that SO3 is defined is that it is the, I mean, intuitively at least it should be clear, and it's not very hard to prove that any point on the two-sphere can be reached from any other point by making a rotation, which is, in SO3, right? So this is also a transitive action, right? The action of G, if X is some element, is S2. For convenience, I'm writing X as a set of three numbers, but which, so maybe I should say X is an element, is a position vector with its norm given by 1, right? So that means X points, it's the end of the end point of the X vector is on S2. And we know that any point on S2 can be reached from any other point by a suitable rotation, right? So this acting on X, so this action is a transitive action. Okay, this is basically the exercise I gave you. Any questions about transitivity? Now let's take an example which is not transitive, right? Because to understand something, you have to understand the counterexample. And the counterexample is this. So if I take a two-sphere, and this is a two-sphere, and if I consider the rotation around the z-axis, okay? So that is also an action. So this is also an action, right? So here what we do is that we take G to be of the form of, say, cosine of theta, cosine of theta minus sine of theta 0, sine of theta, cosine of theta 0, 0, 0, 1, right? So this is a rotation around the z-axis, right? So this is going to be an element of SO2. So it also acts on the two-sphere. But what it does is that, given a latitude, it can only take us to other points on the same latitude, right? So the group, this group SO2Z, cannot change us, cannot take one point from one latitude to another point on another latitude, right? So it cannot take us in this direction. That's not allowed. Is that clear? This particular group.
Yes, sir.
So here we see an action which is not transitive. So this action is not transitive on the two-sphere. If I take G to be SO2 around Z and M to be S2, then the action G of X, X prime, is not transitive, right? Okay, so now you understand what transitive action is, and you also understand what transitive action is not. Any questions?
No, sir.
Okay, anyone else?